Hi. Today we're continuing our discussion of chemical reactions. Specifically, our focus is on single replacement reactions and this new term, spontaneity. So as before, we're going to watch this video. It's going to give us some information, so you jot down any questions that you have, any observations you make. I'll do the same. Oh, so there's a hole there. All right. So full disclosure, this is something you can do at home. Oh, look at that. It's hollow. Oh, and it's crinkling like there's foil. So he hollowed out the penny. Huh, go figure. Full disclosure, this is something you can do at home on your own. All you need to do is get a penny after the year 1982, and you could do it with vinegar. It just takes a really long time. But let's talk a bit about pennies. I don't think pennies should exist. Just going to go out on a limb and start by saying that. There's a wonderful, long, tangent I could make on that. I'm not going to do that now. If you want more information about why pennies shouldn't exist, and I agree with everything on this video, there's a CGP Grey video. If you're not familiar with the YouTuber, I will include a link to his video in the description. Outlines everything wonderfully, but here's what we need to know. In 1982, the cost of making pennies became too large. The government actually has to buy the metal from suppliers to make pennies. Up until 1982, pennies were 95% copper, 5% zinc. Those mixture of metals gave the properties that we wanted, the appearance that we wanted. But around 1982, we finally decided that that was too expensive. So we didn't get rid of pennies. Instead, we changed the recipe. We still want the copper. There are certain benefits to the copper that we'll actually talk about today. But in addition, like the zinc was cheaper, so we had to increase the zinc. So now I think the best way for you to picture what a penny is kind of like an M&M or an egg. For an M&M, where the candy shell is made out of copper and the chocolate filling is made out of zinc, this is a penny. Here, obviously, this is what a penny looks like. If you sand off the face, you get this silvery metal on the inside. Here, people have snipped them in half so you can see that the inside is mostly silvery gray. It is made of zinc. This means that when a penny, like the penny we saw in the example, has a little hole carved in it in the side, you're exposing that zinc. So in the solution, there was both zinc metal and copper metal exposed to whatever was in that liquid. And so here's another picture of it. This picture is probably a fair deal sharper to really drive that home. Now, I don't think pennies are completely useless. I think they have wonderful applications, specifically to chemistry teachers, as a good source of cheap copper metal and cheap zinc metal if you want to do that sanding. What we have here is actually, if you make a pile of these sanded pennies, you can make a rudimentary battery. This one, it's got some nickels in there too, because nickels actually, they contain some nickel, about 3/4. And you can actually stack them, and based on the properties of the metals, you can get electricity to flow from the top to the bottom or the bottom to the top of the pile of pennies, which is great. But we're not talking about that today. Specifically, we're talking about the fact that this part of the penny is made of zinc, and this part of the penny is made of copper, and clearly there's a different result where these holes exist. You're seeing bubbles come out. Yeah, there are bubbles here on the top, but those bubbles are kind of a side product of the bubbles that are coming out there. It's the hole and what's happening there that's the most important. So as a quick review of single replacement reactions, the general form is an element reacting with a compound to make an element and a compound. The one thing I didn't make a big deal about before that I am going to say now is that two things. One, the compound, for the purposes of this course, will be ionic. So it's an ionic compound reacting with an element. Now that means that the element that you're reacting the ionic compound with might interact with the ionic compound differently based on the properties of the element. And that's shown up here. Since an ionic compound is a metal and a nonmetal put together, if you're reacting a metal, the metals actually end up reacting with the metals, or if it's a nonmetal, the nonmetals will actually end up reacting with the nonmetals. So here are two general forms. I've got several examples below. Here we've got zinc reacting with iron 3 chloride to make zinc chloride and iron. We have iron 3 chloride reacting with aluminum to make aluminum chloride and iron. We have calcium chloride reacting with fluorine to make calcium fluoride. So in this case, the zinc is actually popping out the iron. You can see that where there was an iron now is a zinc, and the iron is kicked out as an element. The aluminum reacts with the iron and kicks it out, giving us aluminum chloride and iron. And then in this case, since fluorine is a nonmetal, it will pop out the nonmetal, making calcium fluoride and chlorine. You may be noticing that there are some coefficients showing up in this first reaction. We'll talk about that in a few slides, but we do have to worry about balancing in chemical formulas. I thought it best first just to focus on the general form of element bumping out element in compound. That said, there is something worth mentioning here, and this is the first time we've talked about this. I know we're kind of new to chemical reactions, but there is this idea that not every chemical reaction that we write on paper can take place. Just because we write it doesn't mean it happens. So these are two examples on the bottom. You'll see here I copied over, let me change colors. I copied over the products. One of the interesting phenomenon of single replacement reactions is that if you take the products of your single replacement reaction and attempt to react them, if I went, you get your iron 3 chloride and your zinc and you put them together and you see something that happens kind of like what you maybe saw in the penny in the acid. I have a different. This is another example of what it might look like without the bubbles, without the acid, which, by the way, spoilers, that's what's in the solution. This would be a reaction between zinc and lead nitrate. So again, element and compound. The zinc is a metal, the lead is a metal, the zinc replaces the lead in the metal, and you get elemental lead. And that's it's marked trees. These little spiny bits that are growing off of the piece of metal are lead metal. The piece of metal in the back is, again, that shiny, that gray zinc. So we get this process where you can actually see an element be kicked out and start to form on the surface of the element that you put into contact. For these down here, we've got the nonmetal, but when you try and take, like these products, if you put lead metal into a zinc nitrate solution, nothing happens. If you try and take zinc chloride and react it with solid iron, nothing happens. There is this one-way quality to these single replacement reactions where the opposite doesn't happen, and we call that non-spontaneous. So there must be some sort of guiding principle that says which reactions do and don't happen. And of course, that does exist, and it's called Table J, known as the activity series in your reference tables. So there's a link to the reference tables above my head, upper right-hand corner of your screen. The word activity here is going to be a relative measure of the reactivity of your elements, how likely an element is to be in a compound. I don't really want to get more into it there. There's some more that we're going to talk about in future units, but there it is. So to determine the spontaneity of a chemical reaction, you have to look at the element in the reactants and its corresponding element in the compound. That is to say, the metal or the nonmetal. So I'm just going to underline really quick. We're less concerned with the other part of the compound. If there are two metals present in the reactants, we're not concerned with the nonmetal. But what we're doing is we're comparing the relative activities of the elements found on this activity series. It says at the top we have metals and nonmetals, the most active at the top, the least at the bottom. So between zinc and iron, here's zinc. Zinc is more active than iron, so that means yes, the reaction happens. between aluminum and iron, so I'll erase the zinc. Between aluminum and iron, aluminum is more active, so yes, the reaction happens. Between fluorine and chlorine, we can see the two of those right there. Fluorine is more active, so yes, the reaction happens. If the products will show the more active element in the compound, then yes, the reaction happens. If we take a look at these bottom two here, those flipped reactions, we'll see that iron, the element, is now lower on the activity series than both aluminum and zinc. So when aluminum tries, for lack of a better word, to bump out the zinc, nothing happens. So that's basically the conditional nature. It involves going to your table, taking a look at those elements, comparing them, and if the more active metal is an element in the reactants, then the reaction happens. If the more active metal is in a compound already, nothing. This feels like it could immediately lend itself to saying, well, you can then predict whether or not a reaction can happen based on just the reactants themselves and table J. So that's what we're going to do. Same process. I'm just going to underline the relevant parts, right? Here are all our elements. And then the corresponding element in the compound, we've got metal, metal, non-metal, and some metals. And we're just going to compare them. I actually think it would be good before we write any products, just to go down and I'm going to put a check mark next to the ones that do happen and an X next to the ones that don't. If you want to do that yourself, by all means, pause, take a look at table J here, figure it out for yourself. All right, so I got that 5 out of the 6 of them do happen. This 5th one does not. So here we're going to write no reaction. So we're kind of done with that 5th one. Let me clear things up. In each of these, I see that there's a Cl4 here, but nature does not appreciate convenience. Just because you see 4 chlorines in the tin 4 chloride doesn't mean that when aluminum pairs up that you're going to see AlCl4 plus Zn. That doesn't happen. This isn't the compound that's made between aluminum and chlorine. So while there is a switching, you have to make sure that the elements that you write are true to the swap rule and true to the ion ratios that need to happen to make this a neutral ionic compound. This means you kind of need to step back and do a little bit of review. We know that aluminum from our reference table has a 3+ charge, chlorine has a 1- charge, so when you swap those, the compound that you get here is AlCl3, not AlCl4. I get that there's a 4 there, but that's the compound that's made between aluminum and chlorine. So let me clean this up. And then you would take a step back. Why did I write zinc? I meant to write tin, sorry. And then you would take a step back and balance what's here. We're going to say that for each of the ionic compounds, they are aqueous, dissolved in water, like we saw in the video. And then all of the elements are, of course, they're metals, they're solid, they're nonmetals, they're usually gases. But let's balance. There, nice. Same thing, right? So we're going to take a look at zinc. Zinc is a +2 ion. Chromium bromide. Well, the chromium's a transition metal, but if we unswap, we get a +2 there. But really, I'm mostly concerned with this Br. The Br there is going to be a Br-. So the compound that we're going to make is ZnBr2, and then elemental chromium, obviously. Sometimes it does work out that for these single replacement reactions, if both of the metals involved have the same ionic charge, then yes, it's already balanced. We're actually done. That one's good. So I'm going to move on and do some of the more of these. If you want to work through these on your own, you can, and then you can check your answers with me when we're done. You will never see a single replacement reaction and its opposite both happening. It's always one or the other. So for the 4th, 5th, and 6th, you could have seen, if they're opposites of each other, then one's going to work and one isn't. Here are our products. I need to go through and balance really quickly. So I think that's balanced. In each case, even with a polyatomic ion, you still do the same thing. Figure out the charge of the anion, cation between them, the neutral compound. Write your products, then balance. So to bring things all back together, I think we do need to take a look back at the video. In the video, we know that pennies are made of copper shells and zinc insides. So those two aren't going to react with each other. They're both reacting with whatever's in the liquid. Obviously, when you hold a penny, it's not actively reacting. It's when it gets put in this liquid. And I'll help you out here. This liquid is actually a solution of hydrogen chloride, otherwise known as hydrochloric acid. You'll notice that H2 shows up on our activity series here, and that there's a little thing at the bottom corresponding to this activity series, right? Based on the hydrogen standard, and it says explicitly, even though it's in the category, hydrogen is not a metal. However, in binary covalent compounds that have hydrogen paired with another nonmetal, the hydrogen acts like a metal in many cases. Hell, sometimes in water, hydrogen acts like the metal. And I'll show you an example of that after this. But what we have here is actually two different potential reactions. For each of these, we have our hydrogen shown, but we also need to compare them to the element that is reacting with the hydrochloric acid. So we have copper in one case and zinc in the other. Now you can see that hydrogen's found in between zinc and copper. Remember that I said that we kept the copper coating on the penny for a reason, even though the copper was more expensive? This is it. Copper is less active than hydrogen. This means that when copper gets introduced to compounds that contain hydrogen, these binary compounds, no reaction occurs. Since copper is lower, this is no reaction. And afterwards, you still have copper and hydrochloric acid. The zinc is more active. The zinc will replace the hydrogen and kick it out. So our products here, zinc is a +2 ion, will be ZnCl2. And remember that, Brinkelhoff, right? Hydrogen as an element is one of the diatomics. And then we have to balance. We're balanced. So this kind of explains what we saw in the video. No, it doesn't kind of. It does. The zinc on the inside of the pennies reacts with the acid. The copper on the outside of the pennies does not. So if you want to do this at home, take a penny, put a little score in the side of it, and let it sit in vinegar for a day or two. Maybe you need to replenish the vinegar once or twice. But you'll actually get a hollowed out penny, and it will just be copper foil, basically, that you can crinkle and crunch and play with. And it still has Lincoln's face on it and everything. It still has the detail, but it's very, very thin. You can do that yourself. Let me know if you get something usable out of it. I did mention water, and I did want to specifically speak about that because we watched a video of the alkali metals reacting with water, and it works much the same way. If we rewrite water as HOH, that kind of makes it look a little bit like these compounds here. It's not binary. Well, it is and isn't binary. It's like this polyatomic ion hydroxide that we saw before is there. So you can see reactions. This one is lithium between very, very active metals, the ones found at the top. You'll notice that's a lot of group 1 and group 2 elements, reacting with water. And it will bump out this hydrogen to make lithium hydroxide and hydrogen. You'll need 2s in several locations to make this balanced, this being aqueous and this being a gas. And when you saw those metals bubbling in the presence of water, those bubbles are hydrogen gas. Of course, it's flammable. Of course, it's dangerous. So if you do this at home, make sure it's a well-ventilated area. But this is another example of a single replacement reaction where these metals are actually reacting with the hydrogen in water. And this also might give you a little bit of a hint why so many of our pipes are made of copper. Originally, they were made from lead. They're a little bit easier to work with, but lead slowly reacts with water, and copper does not at all. So to sum things up, use Table J. In case you didn't catch that, use Table J. So single replacement reactions, an element and a compound react to make an element and a compound, but there is this conditional of can it happen? Reactions can only happen if the metal, the element reacting with the compound, is more active than the corresponding element, the metal or nonmetal, in the compound of the reactants. So it's all written out there. This is everything we've seen before. And by the way, you may need to use your swap rule, of course, to figure out the compounds, the chemical formulas of the compounds before you balance. But usually you'll get that information. So if it's not clear already, use Table J. It's important. It's helpful. Thanks for watching.